So, last class I have discussed about the foundation on collapsible soil. So, today I will discuss the foundation on another type of difficult soil. So, that is the expansive soil. So, now that many plastic clay soils considerably due to addition of water and shrink due to loss of water. So, foundation on this expansive type of soil are subjected to large uplift due to the soiling. So, when the soil soils, it provides a large uplift into the soil. These forces causes heaving, cracking and breakage. So, we have to design our foundation suitably or to tackle this type of soil. Now, how we can understand whether soil is expansive soil and what is the degree of expansion. So, there are number of methods or number of criteria are there. So, I am giving one of them. So, that is the modified free soil index. So, here the 10 gram of oven dry soil is taken and it is transferred to 100 millimeter graduated jar with distilled water, and the sediment volume is measured after 24 hours. Okay. So, the sediment due to the soiling of the soil. So, that sediment is measured after 24 hours. Then the modified free soil index is calculated by using these equation, where V is the soil volume after soiling, okay, and Vs is the volume of solid, and that is weight of solid, that means the oven dried soil, divided by Gs, which is Gs is the specific gravity of soil, and gamma W, which is unit weight of water. Now, if this modified free soil index value is less than 2.5, then the soiling potential is negligible. If it is 2.5 to 10, then it is moderate. If it is 10 to 20, then it is high. If it is greater than 20, then it is very high. So, based on that, we can understand or we can determine the soiling potential of the soil. Now, once the soil is the soiling type of soil, then our expensive soil can be replaced below the foundation. Then changing the expensive soil, okay, so we can provide the compaction, P-wetting, installation of moisture barrier, chemical stabilization, stabilizing the expensive soil by pressure injection. Okay. Strengthening the structure to withstand against the heave, because as I mentioned, because of this uplift there will be heave. So, we have to strengthen the structure, so that this heave can be this structure can withstand during this heave also. The make structure flexible enough to withstand the differential settlement, differential soil heave without failure, and construction of deep foundation below this depth of active zone is recommended. Again, that as I mentioned, in case of collapsible soil also, we can provide deep foundation and we can provide foundation below this active zone. So, we can provide say such foundation such as pile. So, I will discuss that two types of foundation that can be provided. So, for this soiling or the expansive type of soil. So, that means here the soil will expand due to the soiling. So, there will be a uplift, and then at the same time there will be a downward force also. So, we have to check, we have to provide the foundation in such a way, or we have to provide in such type of foundation that it can sustain or it can withstand again the uplift as well as the compressive load. So, that means it has sufficient amount of compressive load carrying capacity as well as the pull out capacity. So, I will discuss two types of such foundation. Those are suitable or those are generally used for the expansive soil. So, one is the drill shaft, with bells and grade beam. What is that? So, suppose if this is your active, so okay, so let us start that. So, we are providing the shaft with an enlarged base. With enlarged base. So, and then another one with an enlarged base, and then these shafts are connected with beams. Okay, so this is the beam, and these are the active zones, say, or this is the active zone. Active zone means here the soil is an expansive soil. Okay. Now, how I will calculate the, or I will check whether this type of foundation is suitable or not. So, to do that, so suppose this is my active zone, and here we are taking one particular one single shaft, where this is the dead load D, and this is the thickness of the active zone is say Z, and ds is the diameter of the shaft, and dv is the base diameter. Okay, so now the uplift force that will subjected due to swelling is pi ds into z small p t tan phi ps. Okay. So, z is the thickness of this active zone, ds is the diameter of the shaft, and what is pt, what is phi ps. So, I am writing that ds is the diameter of the shaft, then z is the depth of active zone, phi ps is the soil friction angle which is generally taken as 10 to 20 degree. Okay. And the Pt is the pressure for 0 horizontal swell. So, the value of the Pt can be determined in the laboratory. How this Pt is determined? So, first step is that we take the soil sample in a consolidation ring, and then we have to apply a P0 and the PS. Now, let me write what is actually Pt. Pt is basically summation of P0 plus Ps plus P1. Okay. So, now what is P0? P0 is the effective overburden pressure. Okay. Then PS is the approximate anticipated surcharge due to the foundation. Due to foundation. So, that means first you have to apply the P0 which is equal to effective overburden pressure of that site, and then we have to add additional amount of stress which is coming due to the foundation, and then P1 is the additional pressure added to prevent soiling after addition of water. So, what does it mean? So, this PT is the amount of pressure that is applied to prevent the soiling. So, suppose if I apply the stress, because of when water is added, so this soil starts soiling. Okay. So, now if I apply stress, so we can prevent that soiling. So, that stress is PT. So, the PT is the summation of P0, PS plus P1. So, that means first it is placed in a oedometer ring, and then the P0 is applied, which is the effective overburden pressure. Then the PS is applied, which is the anticipated surcharge due to the foundation. Then the soil water is added into the soil. So, that means now under this stress, this stress is not enough. So, under this stress also this soil will start soiling. So, and that condition, so gradually a load or stress is applied up to P1 such that there will be 0 amount of soil. So, that means that to achieve that 0 amount of soil, total stress is equal to PT, which is summation of P0, PS and the additional stress P1. So, this we can determine in the laboratory this PT value. Okay, then sometimes if this laboratory value is not available, then it is recommended that you can use PT tan phi PS, this term equal to Cu. But I would say that you do the test and get this PT value in the laboratory, and then you use this PT value here. So, next one is that Q net. Okay. So, what is Q net? The ultimate load carrying capacity of the shaft, because here we have applied the drill shaft, and drill shaft where we have given the extended base width. So, that is bells. Okay. So, this extended base width, what will it will help that when there will be a uplift, then there will be uplift, this extended base will give us the resistance during the uplift. This extended base, this side one, two sides of the shaft, but when there will be a compressive load, then also this extended base will give the resistance. So, that is the advantage of providing this extended base. So, this will help for uplift as well as under compressive load. So, now we can say that Q net load carrying ultimate load carrying capacity. Okay, so that will be CUNC divided by factor of safety, then pi by 4, then dB square minus dA square. So, which is nothing at CUNC into A, and which area we are taking? So, area of this extended base portion, the shaft portion you are not taking, we are taking the extended base portion, because it is under uplift. Okay. So, this is the net ultimate load carrying capacity. So, this is under uplift, and this is the factor of safety. So, finally, that Q net should be equal to the uplift minus dead load, because uplift force is, or here I should not say ultimate, that this is allowable or safe. This is allowable, or I can say or safe load carrying capacity under uplift, because it a factor of safety is applied. So, Q net is U minus D, or I should write that the Q net that we are getting plus dead load, that should be equal to the uplift force that pile is subjected, because these two forces are acting in downward direction. Only this is this, here it is acting in upward direction, which is U, and this is the D, and here it is Q net. Okay, so, Q net plus D should be equal to uplift. This uplift is due to the swelling. So, here NS is equal to 6.14. Okay, and then Cu is the undrained cohesion. So, now I will solve one example problem, that in a shaft so dead load plus live load is equal to 1300 kilonewton. That means, dead load is 800 kilonewton, live load is 500 kilonewton. This is dead load, this is live load, and the active zone is 6 meter. Is 6 meter. Diameter of the shaft is 1 meter. So, that means, ds is 1 meter. Now, what would be the dB that we have to find? So, this is the bell. Now, the depth of the shaft below the active zone is 3 meter. So, and then other parameters are given. PT is given, which is measured in laboratory, is 500 kilonewton per meter square. Phi PS is it is 10 to 20 degree. So, we have taken average value of 15 degree, and undrained cohesion is 400 kilonewton per meter square. So, these are the values are given. So, the uplift force, okay. So, the uplift force U is equal to pi ds z PT tan phi PS. So, this is 3.14, ds is 1, z is 6, PT is equal to 500 into tan 15 degree. So, this is 2524 kilonewton. Now, assume now for the first we are not taking the dead load and live load effect. So, we are taking this is 0. So, if this is 0, dead load is 0, that means the Q net will be equal to uplift. So, uplift will be equal to Q net, that is CUNC factor of safety pi by 4 BD square minus DSS square. So, this U will be CU is 400, NC is 6.14, factor of safety say we are taking here 2.5. So, we are taking factor of safety is 2.5, okay, and this is pi is 3.14 divided pi is 3.14 divided by 4, and then dV square is we do not know the value of dV. So, dV square minus 1. So, now this will be equal to U is this is equal to 2524. So, if I solve this, then I will get the dB is equal to 2.1 meter. Okay, so, for this trial take our dB value is 2 meter for first case. Now, we have to calculate the factor of safety considering uplift dead load also, because actual equation is Q net is equal to U minus D, but we have neglected the D for this particular case. Okay. So, we are now calculating the factor of safety. Factor of safety for uplift. So, that is CU NC pi by 4 dV square minus ds square divided by, because here this is Q n. So, if factor of safety means this term divided by U minus D and factor of safety will go this side. So, this is U minus D. So, this is 400 into 6.14 into 3.14 divided by 4, 2 square minus 1 square divided by 2524 minus 800, because live load we are not considering right now, because live load may not be always present in its maximum value. So, this is equal to 3.4, which is greater than 2.5. So, okay, or safe. Okay. But now, as I mentioned, we have to check it for both uplift as well as the compressive load. So, this is this uplift we have checked. Now, we have to calculate the factor of safety for compressive load also. So, now we know that D plus L is 1300 kilonewton. Okay. So, the stress which is acting is 1300 kilonewton divided by pi by 4 into B square. So, this is 414 dV square we have taken, kilonewton per meter square. Now, Q ultimate will be CUNC for that particular soil. So, now we are calculating the this stress or the load carrying capacity under compressive load. So, under compressive load total BD you have to consider, and we are not considering the friction resistance, we are taking only the base resistance. So, base resistance in uplift will be only the enlarged portion, we will not consider the shaft region. but for the compressive load you will consider total diameter of the base. Okay. So, and that equation is Cu Nc. So, Cu is 400, Nc is 6.14. So, this is 2456 kilonewton per meter square. So, what will be the factor of safety? So, the factor of safety will be factor of safety under bearing or compressive load is equal to 2456 divided by 414. 414 is the stress which is acting and 2456 is the load carrying capacity or stress carrying capacity. So, this is 5.9 which is greater than 3 safe. But you can say under uplift also it is 3.4 and it is 5.9. So, slightly higher value. So, we can further reduce the dV value. So, how we can take the dV value? Now, if we take in second trial the dV is equal to 1.8 meter. So, factor of safety under uplift the same way we can calculate will be equal to 2.5 which is greater than or equal to 2.5. So, it is acceptable, and the factor of safety under bearing will be equal to 4.8 which is also greater than 3. So, both are safe. So, we can provide a width of the shaft, base width of the bell is 1.8 meter. So, and remember that we have not considered the friction resistance, because friction resistance is most of the zone is the active zone, and so that active zone is given only the uplift. So, next type of foundation that we are considering the under rem pile, which is very famous in India. Okay. So, in this under rim pile, so this is the under rim pile where there will be a bulb. Okay. So, which is similar to the drill shaft that I have discussed with the enlarged base. Here also this bulb will act as the enlarged base and will give you the resistance against the uplift as well as the bearing. So, this is the diameter of the shaft ds and this is the diameter of the bulb. Okay. And this is say the active zone, which is Z, and where weight of the shaft is also is there, weight of the pile. So, this is zone of seasonal volume change, because it will swell as well as shrink. Okay. So, now these values are, this is the values of different values I am giving. So, first this bulb center, the lower bulb center should be 0.55 ds. Okay. So, this one is ds by 4. Okay. And this angle is phi 1 and this angle is phi 2. Now, generally this phi 1 is close to 45 degree and phi 2 is close to 30 degree. This figure may not be in proper scale, but you should know that. So, these are the recommendation as per IS 2911 part 3 1980. Now, there can be a multi bulb or two bulbs case also. So, this is say one bulb and this is the other bulb. Okay, so this distance between two bulbs, that is called L. So, again this is the Z is the thickness of the seasonal change, and here I will explain why these dotted lines. Now, here ds is generally recommended, or the range is ds of 2000 to 200 to 500 millimeter ds, and dB by ds is 223, or this is equal to 2.5, which is the average value. That means the bulb diameter is around 2.5 times more than the shaft diameter. Okay. Now, this L is roughly 1.25 dB to 1.5 dB. So, the L value roughly this spacing between the L is in between 1.25 dB to 1.5 dB. Okay, and this again this value is ds by 4. Now, the uplift capacity of the two bulb case will be AP NC CUP plus AA NC CU A dash plus CU A dash, then AS dash plus alpha CU A AS. Now, what is this term? Let me explain. So, these two terms are giving the bearing, and these two terms are giving the friction, because here the friction is also considered. Now, this is not for the uplift, this is actually under compression. Now, where AP is equal to pi by 4 ds square, NS or NC is equal to 9, CUP is the cohesion or undrained cohesion around the base, AA is pi by 4 dV square minus ds square, alpha is equal to taken as adhesion factor, which is 0.5, and AS dash is the surface area of the cylinder between two bulbs, that is equal to 2 pi dBl and AS is equal to surface area of the steam. So, let me what is that? So, first part is APNC CUP. So, that means that this small portion or I am talking about the two bulbs case. So, this small portion, this you will give us tip resistance. So, that small portion tip resistance is APNC CUP. So, CUP is the unit cohesion at this portion, AP is the area which is the dA square into pi by 4 and NC is 9. Then the next portion is this bulb, this outer portion, this bulb, this will also give you the resistance. Okay. This is under compression and this will give under tension. Okay. So, this will give understand for multiple bulb. So, that means it will give the tension resistance here. Single bulb it will give here and it will give under compression. Okay. So, that means here under compression this will give you the tip resistance, the bulb portion. So, that is the second part where AA is the beyond that sharp portion of that bulb is considered, and here NC is again 9 and alpha and this is the cohesion at that region. Okay, so, this cohesion is at that region. So, that means in this region this is the cohesion CUP, here the cohesion is CUA dash, here is cohesion is CU, here is cohesion is CUA dash. Now, the next portion is the friction. So, where this friction is getting? Suppose we have a bulb, when there is a uplift or compression, then the soil within these two bulbs, they will form a cylinder in cylindrical shape of the soil and they will either deform or it will go upward direction. So, there will be friction between soil cylinder and the outside soil. So, here this along this dotted line there will be friction will develop. So, that friction will get that this periphery is pi dB and the length is L and then the cohesion at that point, and at this is friction between soil and soil. So, alpha value will be 1. So, that is why alpha is taken 1, and then the above the second bulb. So, there will be the friction between the shaft and the soil, and that is the AS is the surface area of the steam. So, this is the steam and the cohesion at that point at that value and the alpha which is taken 0.5. So, this is two bulb under compression case. Now, I will just show you another 3 cases, then I will finish this class, and then that means for uplift for two bulb case. So, this is uplift, this is compression. So, uplift there will not be tip resistance for the shaft, but there will be tip resistance from this bulb portion. So, that is the advantage of providing the enlarged base. So, that means for uplift the equation will be AANC CUA dash, I mean first term will not be there, other 3 times will be there, plus CUA dash AS dash plus alpha CUA, this is also CUA into AS. This is for uplift 2 bulb case. Okay, that means the shaft, that means steam friction resistance will be there, this cylinder will be again there, but only the direction of the friction will change, soil cylinder, but only the tip portion resistance will not come into picture. Then one more 2 case. Now, for single bulb, under compression So, single pulp under compression. So, there will not be this frictional part will not be there. This frictional part for the cylinder will not be there, but for the shaft will be there, because this zone there will be friction. Okay, this zone there will be friction along the shaft, but this cylinder will not take place in case of single bulb. So, the equation will be AP NC CUP plus AA NC CUA dash plus alpha CUA A dash AS. So, that means the only the second third term will not be there. First term will be there. There will be a tip resistance due to the shaft portion. Then there will be a resistance, tip resistance due to the enlarged base portion. Then the friction resistance for the steam, they will be there. Now, the last case, that for single bulb under uplift. So, under uplift, okay, so under uplift there will be plus W will also be there, because W is also acting in the downward direction, which is the weight of the pile, weight of the pile. So, for uplift single bulb, third term will not be there and the first term will not be there also, only there will be second term and the third term. So, this will be AA NC CUA dash plus alpha CUA AS plus W. So, these are the 4 cases for single bulb and the 2 bulb case I have discussed under uplift as well as compressive. So, remember that here we have to check both the condition under uplift as well as the compressive, and providing the enlarged bulb is the advantage. So, now I have finished the total course, and these are the list of books or the reference. So, these books I have used to prepare my notes, and I have given their name inside the lectures also, where I have used their material, and these are the name of the books, that means the Principles of Foundation Engineering by B.M. Das, Foundation Analysis and Design by Bowles, then Pile Foundation Analysis and Design by Paulus and Davies, then Elastic Analysis of Soil Foundation Interaction by Salvadori, then Beams on Elastic Foundation by Hetini, then V.N.S. Murthy for Geotechnical Engineering, Principles and Practice of Soil Mechanics and Foundation Engineering, then Ranjan and Rao, the Basic and Applied Soil Mechanics, then Rees and Van Impe for Single Pile and Pile Groups under Lateral Load, and lecture notes of Professor Siva Kugon, James Cook University, Townsville, Australia. So, these are the references, and few references I have used inside the text, inside my lecture. So, those detailed references you will get from these books or these references. So, you can get these things. So, that is it. So, that is the end of this course, and I wish you best of luck for the exam. Thank you.